What I'd like to do in this session is to talk about recursion, which is the engine of computation in a functional programming language. It's the way that we can do iteration, it's the way that we can do complex computation. And what I'm going to start off by doing is describing primitive recursion over the natural numbers. But let's begin this by looking at an example and telling a story. So the factorial function is the function that takes all the numbers from 1 up to n, including n itself, and multiplies them together. What I'm going to do is draw a table of factorials, and we'll learn something from that, and then we'll turn that into an insight about how to do computation in Haskell. Right, let's turn to our table and let's get started. Let's start with the line 0, because conventionally the factorial of 0 is 1. And then for the number 1, the factorial is 1. For the number 2, the factorial is 1 times 2, which works out to be 2. For 3, the factorial is 1 times 2 times 3, which works out to be 6. For the factorial of 4, the answer is 1 times 2 times 3 times 4, which is 24. Now you can see there's some repetition going on here. I work out 1 times 2 to give 2. I work out 1 times 2 times 3 to give 6. I work out 1 times 2 times 3 times 4 to give 24. In working out the factorial of 4, I work out the factorial of 3 and then multiply it by 4. So I can go from one line to the next simply by multiplying by 4. Previous line I could get by multiplying by 3. So in general, you can see that I'm making the observation that n factorial is n minus 1 factorial multiplied by n. And that insight that we can get from one line to the next gives us a way of efficiently calculating this table of factorials. So we've got the insight that we can build each line from the previous one, and we can turn that insight into a definition in Haskell, which says factorial of n when n is 0 has the value 1, otherwise when n is bigger than 0, it's the factorial of n minus 1 times n. So that is describing this table of factorial numbers, starting at 0 and giving one number and then the next. But we can turn this around and see this actually gives us a way of calculating factorial of n for any non-negative n. Here's our function definition, and we can use that directly to build a calculation in Haskell, and so build an implementation of this recursive function definition. Let's see that now. Here's the definition of factorial of n, and let's do an evaluation. What is factorial of 3? Well, the first guard doesn't hold, so we use the second, which says that it's 3. Let's start again. Let's work out the factorial of 3. The first guard doesn't hold, so we use the second, which tells us that it's factorial of 2 times 3. Now, in order to work out that, we need to know the value of factorial of 2, which is factorial of 1 times 2, all times 3. And similarly, factorial of 1 we need to know, and that turns out to be factorial of 0 times 1 times 2 times 3. And now we know the factorial of 0, which is 1. And in fact, you can see that this calculation has given us explicitly the way we've written it out, the formula for factorial, which if we do all the multiplications, it gives us the answer 6, which is indeed the factorial of 3. But the point I wanted to get across here was not that it's a great discovery that factorial of 3 is 6. It's that we can use equations like this, recursive equations, to do calculations. And the mechanism for implementing recursion in Haskell is just like the mechanism for calculation we've seen so far. We simply use that definition to calculate a result, and that gives us, in this example, we can see it's given us the answer 6. Turning back to the presentation, we've seen how we can use this definition as a way of calculating factorial of n for any non-negative n. Now what I'm doing just for safety here, I can add a third clause, a third guard, which says what to do in the case that n is negative. And I'm simply saying that factorial of a negative number is 0. Now this gives us a mechanism for defining factorial. But if you forget about the fact it's defining factorial, what's the general pattern that you can see here? The general pattern is that we give a definition for 0 and that we give an answer for n greater than 0 using the value for the answer for n minus 1. So we define f of n in terms of f of n minus 1. And we also give some information about what happens when a number is negative. But the key thing here is that we describe how to get from f at n minus 1 to f at n. And as you saw when we did the calculation, that's enough to give us the value for every positive number, because the value at 3 depends on the value at 2, which depends on the value at 1, which depends on the value at 0, which is given. So in every case with this pattern, we will have a defined answer. So this template for what's called primitive recursion is one which is very powerful and allows us to define functions over numbers that will always be defined. And what we'll do in the next segment is we'll look at a whole lot of examples. But just to conclude this segment, I wanted to say something about the terminology. Recursion means defining something in terms of itself. That can be, in general, can be complex, and it can lead to an infinite loop or a black hole. A British Prime Minister notably said, Brexit means Brexit, which, while it's true, is not a very helpful definition. It doesn't tell you anything about what Brexit is. So recursion can, in terms of definition, be meaningless. But certain kinds of it obviously work, and we've seen that primitive recursion works very clearly, because if we count downwards from a positive number, we eventually hit 0. So we'll always get an answer using that primitive recursion template. Now we'll meet some other forms later on in the course, but for the moment, what I want to do in the next segment is just run through a whole lot of examples of defining functions over numbers by primitive recursion.